And welcome class. So welcome to the session of the fluid mechanics. So this time we are going to have more examples on hydrostatic force on plane surfaces which are submerged. So let us consider this first example. A square frame 3 meter by 3 meter in dimension is submerged in water vertically with its top 3 meters from the surface. So if this is the top, and that would be 3 meters. If oil occupies the top meter, say this is our water surface, and the top meter is oil, because oil, remember, is lighter than that of water. So this is oil of specific gravity of 0.8, and this has a head of 1 meter. So our task here is to determine the horizontal pressure acting on the frame. So remember, from the center of gravity, we have a location below that by a dimension E to that of the center of pressure, where the hydrostatic pressure or force is located. So P here, remember, is given by gamma h bar A. So remember, in this formula, we should use only a single or a similar liquid. So in this case, we have two different liquids wherein oil occupies the top meter. So what we do here is to get the equivalent head of oil in terms of water. So the top layer should have an equivalent head of water, so that this liquid surface of water will be our reference in the computation of our h bar. Say from the center of gravity up to the liquid surface, that is our h bar. So first things first, we need to compute that equivalent head of water where the oil occupies 1 meter. So what we do is to equate the pressure caused by oil to equivalent pressure caused by water. And then we have gamma h of oil is equal to gamma h of water. So gamma for oil is specific gravity 0.8 times 9.81 times the head occupied by oil 1 meter. And gamma for water is 9.81. We have here the head of water. We can cancel the two terms, and therefore head of water is equal to 0.8. So this head of water again will be our reference in computing for h bar. Hence h bar will be equal to 1.5 meters plus 2 meters plus HW, which is 0.8 meters. So adding all of this, we have an h bar equivalent to 4.3 meters. We now work with this formula. We have P is equal to gamma of water times the computed h bar times the cross-sectional area of the gate, which is 3 by 3. So therefore, P can be easily computed and will equate to 379.65 kilonewton. Okay, so that's it for this problem. So moving on to the next problem. So this is a dam that is 20 meters long. So this is 20 meters long, perpendicular to the screen, and retains 7 meters of water as shown. So this, if this is the liquid surface water, we have here 7 meters. Find the total resultant force acting on the dam. So as an additional data here, so this inclined face of the dam is equivalent to 60 degrees. So of course, what we need here is the total resultant force acting on the dam. So Actually, we are working with a submerged plane which is inclined at 60 degrees. So therefore, we need to compute for this inclined dimension wherein, of course, this will be 20 meters long as its width. So this is 20 meters long as for its width. So we are actually working with this cross-sectional area wherein this is 20 meters long, and then for the meantime I'm going to delegate this as Z. As you can see, Z can be computed using a right triangle. Okay, so on that right triangle, we can illustrate that right triangle. So this is the inclined dimension we need, and this is 60 degrees, and then this is the 7 meters. Hence, therefore, we can relate 60 degrees, 7 meters, and Z by the function of sine. We can say that sine 60 is equal to 7 all over Z. Hence, Z is equal to 7 all over sine 60. Now that we know Z, what we do next is to determine our resultant force. And then, as usual, we label this as our center of gravity. And below that, we have here the center of pressure by the dimension E rather. And we have here the force P, which is one of the unknown. And then the next unknown is what will be the location of this total resultant force. So in the previous problem, we are using E to locate P by adding E to that of our Y bar. Hence, the location is expressed by the variable YCP. So therefore, the unknown in the problem is YCP equal to Y bar plus E. So in any problem on submerged plane surfaces, we need to start first with the calculation of H bar and Y bar. So in this case, remember that Y bar is the distance from the center of gravity, okay, up to the liquid surface along the vertical. So this is our H bar. And then for Y bar, from the center of gravity up to the liquid surface along the inclined or along the submerged plane surfaces, but this time we have an inclined, so therefore this is our Y bar. Now it is obvious that Y bar is just the hypotenuse of the leg H bar. Hence, we can relate by sine function to connect H bar to that of our Y bar. So first things first, we compute for the H bar. So H bar obviously is the half of the dimension 7 meters. So therefore, we have H bar is equal to 7 all over 2. That is 3.5 meters. And then Y bar is simply equal to H bar all over sine of 60 out of this relationship. So therefore, we can just simply substitute in that expression, we have y bar is equal to 4.04 meters. So knowing h bar, we can now proceed with the calculation of the first unknown. Say letter A, P is equal to gamma h bar A. We have a gamma of 9.79 and h bar is 3.5 times the area Z by 20. Hence Z is 7 all over sine of 60 times 20 meters. Noting that this is Z, so we can now compute for the value of P. And then we can get the value of P, which is equal to 5,539.21 kilonewton. So what we need next is the value of E, so that we can now locate our center of pressure from that of the liquid surface by YCP. Now we know that E is equal to I bar plus AY bar. For a rectangle, we have BH cube all over 12 for its centroidal moment of inertia. And the area is given by base times height. Of course, we retain that Y bar. So the base here is 20. And then the height is Z. By the way, 7 all over sine 60, that is equal to 8.08 meters. So we just place it in here, divided by 12, divided by 20 times 8.08 times the computed Y bar, 4.04 meters. So upon computation, we can get E is equal to 1.34 meters. So therefore, we can now work with the second unknown. Say letter B, YCP is equal to Y bar plus E. And that will be equal to 4.04 plus 1.34. This will be the location of our center of pressure up to the liquid surface. And that would equate to 5.38 meters. Okay, so this is the location and the magnitude of the hydrostatic force on this dam. See, moving on to the next problem, the inclined rectangular gate with water pressure on one side is shown. Determine the total resultant force acting on the gate and the location of the center of pressure. So in this one, we have 30 degrees inclined with the horizontal, and this is 8 feet. So these are given dimensions. So if I'm going to label some points here, say this is point A, and that should be point B. Our task here is to determine the resultant force. Of course, as usual, we have this to be the center of gravity, and below the center of gravity is the center of pressure, and we just draw a perpendicular line, an arrow towards the gate, and this is our hydrostatic force by the dimension E from the center of gravity. So again, the unknown here is P and YCP. So the basic thing you need is to get the value of H bar and Y bar. So to do that, of course, we need to consider, actually this is given, this is given in the problem. that this rectangular gate is 5 feet 5 by 4 feet in dimension. Okay, so if this dimension is 4, okay, so h bar can be computed from the center of gravity up to the liquid surface. So of course we consider this dimension, say that dimension is we label that as z for a while, and we can see that z is related to the dimension of the gate, or the width of the gate, and that could be represented by a triangle. Say this is the half of the width of the gate, and the width of the gate is 4 feet, therefore this is 2 feet. So this one up to this point, that is 2 feet, and then this is z, and this is the inclined plus horizontal, that is 30 degrees. Inclined plus horizontal, this is 30 degrees. So by function of sine, we have z all over 2. And by cross multiplication, z will be equal to 2 sine of 30. And that will be equal to 1 foot. So therefore, this composes of our h bar. Hence, h bar is equal to 8 plus z. And h bar is equal to 8 plus 1. And that will be equal to 9 feet. And then y bar obviously is the hypotenuse of your h bar. Hence, h bar will be equal to 9 all over sine 30. That is 18 feet. So, if we have calculated h bar and y bar, then there will be no problem. Okay, so letter E, P is equal to gamma h bar A. So remember that we are in English units. So gamma for English, for a water we have 62.4, h bar is 9, and the area is 5 by 4. So therefore, P is equal to 11,232 pounds. Letter B, we have the location, of course, that refers to YCP, and YCP is, as usual, y bar plus E. And then again, we need to compute for E, given by the formula I bar all over AY bar. So we substitute BH cube all over 12 for a rectangle times base times height times the computed y bar. So we substitute the value. The base here is actually 5, and then the height is 4. This is cube all over 12. We have 5 by 4. The computed y bar is 18 feet. Hence, we can compute this to be E is equal to 0.07. So, therefore, YCP is actually, y bar is 18 plus E 0.07. Therefore, YCP is 18.07 feet. So, by the way, this is feet. So therefore, we can say that the center of pressure is 18.07 from point A as labeled here. Okay, so that's it for this problem. So moving on to the next problem, we have gate AB is 1 meter long and 0.9 meter wide. Calculate the force F on the gate and the position x of its center of pressure. So take note here that we have an angle here and dimensions. So this is 8 meters, 3 meters, 1 meter, 1 meter, and the intervening liquid here is actually oil with S of 0.81, and this is full of oil up to this point. So therefore we can now proceed with our solution. So as usual, we label this as the center of gravity, and below that will be the center of pressure, wherein the hydrostatic force is concentrated. And between that one to this point, this is E, and this is our center of pressure. So again, the unknown here is P and YCP. So as a matter of solution, we need to determine H bar and Y bar. Of course, that is the first thing you need to calculate, of course, from the center of gravity up to the liquid surface. This is our H bar. Okay, now if we know H bar and if we know the angle, therefore we'll just have to relate H bar to that of the Y bar. Okay, to that of the Y bar by the relationship through the sine function. Okay, so in here we can see that the calculation of H bar will emanate from these inclined dimensions. So this inclined dimension, of course, this point, this is 1.5 meter. So if we know that that dimension is 1.5, we'll just have to utilize the triangle. See, I'll just have to highlight that. Say this is 1.5. Okay, you can form a right triangle here. Okay, that one. Wherein 1.5 is actually the hypotenuse, right? Say I'm going to label this as Z. See, we label this as Z. Therefore, H bar is equal to 3 plus Z. As simple as that. And we can relate Z by that right triangle simply that 1.5 is the hypotenuse. So this is Z, and we know that this is the 50 degrees. So by that function of sine, we have sine 50 degrees is equal to Z all over 1.5. So therefore, Z is equal to 1.5 times sine of 50, sine of 50 degrees. So therefore, Z will be equal to 1.15 meters. So knowing that this 1.15 meters, so therefore, H bar will just equal to 3 plus Z. So H bar 3 plus 1.15. So therefore, H bar is equal to 4.15 meters. So if we know H bar again, we can use the sine function for Y bar. So Y bar is equal to h bar all over sine of 50 degrees. Okay, so therefore y bar is equal to h bar 4.15 all over sine of 50 degrees. So finally, y bar is equal to 5.42 meters. Okay. So if we know h bar and y bar, then we'll have an easy approach. So letter E. Say letter E. P is equal to gamma h bar E. And then gamma is 9.79 times 0.81. H bar is 4.15. And then the gate area is 0.9 wide by 1 meter length. So by that, we can solve for P equal to 29.62 kilonewtons. And then by the way, class, from our original figure, one of the unknown is the position x, okay, from the center of pressure. So if this is the center of pressure, x is labeled up to point A. So if this is point A, sorry, I was not able to reflect that one a while ago. So this is point A. Position x is from the center of pressure up to point A. That is the position x. Say this is x. Okay? And on the figure, x is actually half of 1, okay, 0.5 plus E, right? So this is the half of 1, this dimension. So this dimension is half of 1, that is 0.5 plus E. So therefore, x is equal to 0.5 plus E. So that is one of the condition in the problem and one of the unknown actually. Okay. So in here, we need to compute the value of E. Again, by this formula, I bar is equal to AY bar. So E is equal to the base, so of course the width, that is 0.9 times the height is 1 all over 12, and then this is 0.9 by 1, and the Y bar computed a while ago was 5.42 meters. Hence, we can get the value of E equivalent to 0.0153 meters. So therefore, we have a value here, x is equal to 0.5 plus 0.0153, and that would sum to 0.5153 from A. Okay, so that's it for this problem. So moving on to the next problem, we have here a fish pond gate that is 6 feet wide, is hinged at the top and held close by the water pressure as shown. What horizontal force F acting at the bottom of the gate is required to open it? So this is the gate, rectangular in form, okay, and the width of this is given to be equal to 6 feet. say this is 6 feet. So here we label the free body diagram. Say we have here the center of gravity, CG, and this is the center of pressure, and we have here the hydrostatic force. So separating our free body diagram here, say this is the gate, okay, this is the hinge portion of the gate. So on the hinge portion, remember, there will be two reactions there, say RA Y and RAX. So we just assume the direction for that, and then we need to compute this F. Say this is F, and then present here is the center of pressure, or the pressure, or the hydrostatic force acting on the center of pressure. So obviously, if this is point A, we need to take moments at point A, applying that to be equal to 0 so that we have an equilibrium. So therefore, we will be needing here distances. Of course, distances in relation to the moment arm of this P up to point A. And that P up to point A is obviously half of your 9 plus E. Okay, that is 4.5 plus the computed E. So what we need here is the value of P and the value of E before we can proceed to take moments at point A. Anyway, we'll just have to perform this for the meantime. So here, if we take moments at A, we do not have any moment arm at that reactions. Hence, we have a rotation coming from P that is counterclockwise. So P, that is a negative rotation, times the moment arm up to A, 4.5 plus E, okay, and then a clockwise rotation by F, and that is 9 feet up to point A, so that will be equal to 0. So this will now be our working equation. So again, we need the value of P and we need the value of E. So as usual, we need to determine Y bar and H bar. So Y bar is from the center of gravity up to the liquid surface along the vertical. That can be easily calculated. So H bar here is 8 plus half of 9, that is equal to 12.5. Okay, 12.5 feet. Now since our gate is along the vertical, we can equate this to Y bar, because Y bar is on the vertical. So from the center of gravity along the vertical up to the liquid surface is also Y bar, is also H bar. Okay, so with that, we can now proceed to our P gamma H bar A, and then our gamma is 62.4 and the H bar is 12.5 times 6 by 9. So therefore, P will be equal to 42,120 pounds. And then we now proceed to E. Again, BH cube over 12 times AY bar, area is base times height, times the computed Y bar. We simply substitute, and then the area 6 by 9, and then the Y bar, which is also H bar, 12.5. So therefore, E will be equal to 0.54 feet. So we are now ready to proceed with this equation. So this is negative 42,120, 4.5 plus E plus the unknown F times 9, that is equal to 0. So therefore, when we compute that one, F will be equal to 23,587.2 pounds. Okay, so that would be the required force on the bottom to open the gate. So that's it for this problem. So moving on to the next, we have gate AB is 5 feet wide and hinged at the top. So that is point A in the figure, and restrained by a stop at point B. So stop B will break if the force on A reach 9,000 pounds. Determine the critical water depth. So let us have this to be corrected if the force reach 9,000 pounds. So meaning the stop here will have a full capacity or a yield strength of 9,000 pounds. So meaning it will just have a capacity of 9,000 pounds. So therefore, we wanted to set the force at B to be equal to 9,000 pounds at that condition wherein the capacity of this stop will be just limited to 9,000 pounds. Okay. So the same principle here, but this time our unknown at what depth, so that this stop B will just break. So by that condition, if this is the liquid surface, we just need to follow the sequence of our solution, wherein again there will be P here at the center of pressure at location E. So if we need to determine H here, we express all of the terms in terms of H, and of course in this condition we need to involve 9,000 in our equation. So how can we involve 9,000 in our equation? Just the same on the previous problem we had a while ago. We just need to refer to the free body diagram. So detaching this pin connection from the setup, we have this point A and that is point B, and this shall compose of the free body diagram of gate AB. So we label now the forces. First, we have here a vertical reaction at A and a horizontal reaction at A also. We have here the 9,000, and we have here the E or the P, with that to be E, and this to be half of 3, that is 1.5 feet. Okay, so again, we involved 9,000 here by taking moments at A. Summation moments at A is equal to 0. P will have a counterclockwise moment times the moment arm, 1.5 plus E, plus the clockwise moment caused by 9,000 times the moment arm, 3 feet. This will now equate to 0. So if you notice, 9,000 will now be involved in our equation. However, we cannot see yet the main unknown in the problem, H, or the critical water depth. So what we do is just follow the formula P and express it in terms of H. Similarly, we solve for E in terms of H. So let's do it. So P can be solved out of H bar, isn't it? So H bar, we should express H bar in terms of H. And obviously, in the figure, H bar is 1.5 plus, or H is equal to H bar, or sorry, H bar is equal to H minus what? 1.5 feet, knowing that your H bar is referred to what? To the center of gravity, and the center of gravity is the half of the dimension of the bottom of this is 1.5. So therefore, from the liquid surface, we have H up to the bottom. So therefore, H bar plus 1.5, that is equal to H. So hence, okay, so we can write that H is equal to H bar plus 1.5. So we express H bar in terms of H. We have H bar is equal to H less 1.5. So we can also say that H bar is equal to Y bar, since our gate is on the vertical also. So it is understood that H minus 1.5 is also our Y bar. So the next thing we want to solve is, of course, E, the value of E. So the value of E is, as usual, this is I bar all over AY bar. So we take note that we have a rectangular shaped gate here that is 5 feet wide by 3 feet in length. So the base is 5, height is 3, that is all over 12, times 5 by 3, times Y bar, which is H, minus 1.5. So by manipulation, we can have E in terms of H. And then for P, where P is equal to gamma H bar E, we have 62.4 H less 1.5 times the area 5 by 3. So again, P will be in terms of H. So we can now proceed to our working equation here. We just place the value for P. So we have 936 times H minus 1.5 times this term, 1.5 plus E, 0.75 all over H minus 1.5. Perhaps we can express that to a bracket. And then 9,000 times 3 is equal to 27,000. So that would be equated to 0. And then from this equation, we can now transpose 27,000 to the other side. So it will become negative. So negative shall be eliminated on both sides of the equation. And then from this term, we can simplify this inside term on the parenthesis by getting its LCD. Then h minus 1.5 divided by 1, h minus 1.5 times 1.5. So, we have 1.5h. So, we distribute this one, 1.5 times h minus 1.5 times 1.5, that is 2.25. And then for the second term, h minus 1.5 divided by h minus 1.5, that is 1 times 0.75, that is positive 0.75. So this time we both divide by the equation by 936. We have 936 will be cancelled at this side, and 27,000 divided by 936 is 28.85. We also copy this, h minus 1.5. And then it is obvious that this shall be cancelled. So if you notice, we have only h unknown here. By manipulation, we can now get for h equal to 20.23 feet. So therefore, this will be the critical height, exactly 20.23. This stop will begin to break. Okay, so that's it for this problem. Now moving on to the next problem, we have gate AB in the figure is 16 feet long and 8 feet wide. Neglecting the weight of the gate, compute the water level H for which the gate will start to fail. So meaning, in here, we need to determine at what level of H so that it will maintain an angle of 60 degrees, wherein this gate here is connected to a certain weight that is connected to a pulley. So in this, we take note of the action and reaction forces. So on the FBD of the pulley, if part of the problem that W is equal to 11,000, so we isolate the free body diagram of the pulley. We have here 11,000, and of course that force on the pulley will not change, it will remain to be 11,000. And then as a reaction force on this tensile, that would also be equal to 11,000. So we just continue to label our free body. So if this is the center of gravity and this is the center of pressure, we should have a hydrostatic force P concentrated on that location. Having this to be E and this dimension to be half of your 16, we can now take moments at B. So again, this is to involve the force 11,000 in your equation, since that will be our criteria, or that will be the criteria that will depend on the value of H. So summation moments at B is equal to 0. We have 11,000 will have a clockwise rotation times the moment arm of 16 minus the counterclockwise P due to the counterclockwise force due to P times the moment arm 8 plus E. So I'm sorry, reference here is our B. So how shall we determine this from center of pressure up to this point, up to B? So say I am going to label this as Z. So we place that for a while as its moment arm, and that is equal to 0. So Z actually is undetermined. And then, by the way, if we are going to really stick to our submerged portion only, okay, we go back to a portion that is only submerged to the liquid. Say this is the portion submerged to the liquid, and take note, from that submerged portion we have here the center of gravity, the center of pressure, the concentrated force at that certain location, and this is E, and again this is labeled Z. Okay, so we have that as our equation. Now, what is Z in this diagram? If we will consider the triangle on that given this center of gravity, say we will correct that to be the center of gravity is actually the half of H, or the mid of H. Say this is the inclined portion from CG point B, and we just project a vertical line here, and knowing that this is 60 degrees, we know that this is half of H, or H over 2. And then from that we can use the relationship that sine of 60 is equal to H all over 2 all over E plus Z. So by cross multiplication, E plus Z is equal to H all over 2 sine 60. So in here we have H all over 2 sine 60 minus E. And this Z is the moment arm of P. So we are now done with Z in terms of H. So what we do next is to express E in terms of H as well as that of P. So basically, we need to determine H bar and Y bar here. Okay, from the figure, H bar is simply equal to half of H. Okay, and then Y bar will be related by sine function H bar all over sine 60. And then knowing that H bar is H over 2, we substitute it in here. Therefore, Y bar is equal to H all over 2 sine of 60. So working with H bar and Y bar, we can now proceed to write the equation for P, gamma H bar A in terms of H, and then E, we have I bar all over A Y bar. So in here, we should work with the inclined dimension given by this line, and that line could be related to this right triangle, wherein this is 60, this is H, and that is H all over sine 60. So therefore, this will now be our submerged portion. So therefore, this is the area that we need to consider, wherein the length is H all over sine 60, and the given width is 18 feet wide. Okay, so with that, we need to write this. The base is 8 or we write first the formula so that we can simplify the variables. Divided by BH, and that is Y bar. Notice that BH here is cancelled. So what is left here is H squared. And the formula simplifies to H squared all over 12Y bar. So by that, we substitute the value of H as H squared, that is 12, and Y bar is H all over 2 sine of 60. We can actually cancel this one of the H, hence we have 12 over 2 is equal to 6. Therefore, E would simplify to H all over 6 sine of 60 degrees. So working now on our final equation here, we have 11,000 times 16. We can transpose this to the other side, becomes positive. We are now working with P. 62.4. H bar is H over 2. The area is 8 by H all over sine 60. This time we need to have the value of Z. So times the value of Z, H all over 2 sine 60 minus E, H all over sine of 60 degrees. So we simplify these terms. We have 11,000 times 16, that is 176,000. So we divide both sides by 62.4. So we perform that to the left hand equation, and eventually that will be vanished on the right hand side of the equation. So we vanish this one, we divide it to this, and then 8 over 2 is 4. We also do division of both sides of the equation by 4, and then we will have this one, H squared, H times H, that is H squared all over sine of 60 degrees, and then we factor out H on this equation. H are common, right? So we factor out H all over 2 sine 60. So what would be left here is, so we have here 1 minus 1/3. So by manipulation, actually, we can get the value of this. After getting the value of this, we can multiply it by sine 60 by cross multiplication, multiply it by 2, multiply it by another sine 60, and then this one is 0.66. We divide this answer by 0.66, and then we get the cube root. That will be our H, and that would yield to H is equal to 11.67 feet. Okay, so this will be the critical height, so that we will maintain the setup wherein the weight here should be equal to 11,000 pounds, and the inclination here remains to be 60 degrees. Okay, so that's it for this problem, and I hope you have learned a lot from this session, and thank you for listening. Have a good day, class.